master's in geophysics and space physics.
Yep.
And then he went on to an illustrious career, got a PhD in theoretical and mathematical physics at Princeton,
Yep.
I believe. Then was a postdoc with Steve Hawking.
Yep.
Wound up at Microsoft and became the chief strategist and chief technology officer at Microsoft. I think stayed at Microsoft for 13 years or so.
Yeah.
And I guess figured would do something even more interesting, launched his own company called Intellectual Ventures. Nathan's got lots of interests, dinosaurs, asteroids, cooking, photography. And I read his paper on dinosaur analysis a few years ago, and Nathan was sort of challenging some of the methods that had been used and proposing improvements to how it's done. And I think that was beneficial to that community. And then recently, he has been doing something sort of similar about asteroid sizes, asteroid size measured by the NEOWISE mission. And I met Nathan at DPS in 2016, and working at a poster, and I met him again this year, and invited him to come and tell us about this data set and the analysis and maybe how it can be improved. So,
okay.
Very glad to have you.
The greatest treasure trove of information about asteroids that we have. It's got some set of observations on 164,000, and at present there's no even planned mission that will have a 4-band observation or a more than 2-band observation, and there isn't even a 2-band one that's being worked on actively.
How about NEOCAM?
Well, NEOCAM is a 2-band one. NEOCAM has got 2 issues relative to this. One is they aren't really thermal bands. So that's one challenge. And that's because they don't want to have cryogen, because they want to find, it's really about asteroid discovery more than about physical properties.
Okay.
And NEOCAM isn't approved yet.
Yeah.
That's the other thing. So that's what I just said here. It's together the NEOWISE data is about 16 times larger than all previous IR observations of asteroids. So it's an incredible resource, and it's important to understand it. So I actually got into this because the people at the B612 Foundation came to lobby me to give them money for their satellite to find asteroids. And a lot of what they made this presentation to me, I said, this can't be right. So I wound up writing a paper about surveys, how to find asteroids, comparing NEOWISE, NEOCAM, or not NEOWISE, excuse me, NEOCAM, the B612 project, there's a CubeSat project at JPL, there's LSST, and there's a couple of other proposed things. And as part of that, I started working on NEOWISE, because that was a database of properties that are already out there. So, NEOWISE is both in the papers that were there before those, so the original papers, then more recently they compiled them all in the PDS system, which is the most convenient way to get them. Now, that's actually sort of the first issue with this, which is there's actually a lot of differences between the original papers and what's in the PDS. So this is the biggest paper. This is the main belt paper, which has about 130,000 asteroids in it. But there's 3,700 that were in the original that aren't in the PDS. And there's 1,200 or so asteroids that are in the PDS attributed to the paper, but weren't in the original paper. And the main point here is it's very convenient to get from the PDS, and the PDS also has some additional information that's very nice, but it isn't exactly the same, so if you get different results, that's probably why. It's a little strange because the PDS, the documentation is kind of clear that it is a compilation. And this is just examples of some of the things that, that have changed. I think that's probably less important than the next point. Now, I think the other thing is that it's tempting to think of NEOWISE as one big monolithic pile of data, but in fact they had a lot of different models that they used. There's 10 different models across here. And then there's another set of different combinations of bands. So the WISE satellite had 4 bands, W1, W2, W3, W4, in increasing wavelength. So in fact, when you go through it, what you discover is about 45% of the NEOWISE results are NETM-like. NETM is the near-Earth asteroid thermal model. About 55% are STM-like. STM was the standard thermal model. This is a model that goes back to the late 1970s, early 80s, where you fix a parameter called the beaming parameter. In terms of fully thermal bands, it's about 44% of the observations have bands that are thermal. The W3 and W4 bands are long enough wavelength that at typical asteroid temperatures, that's where they're emitting. The W1 and W2 bands have a lot of reflected sunlight, so they're a little hard to interpret. 1% are partial. 51% are based on a single band. Now, that's a little awkward because you can't really have a thermal model based on a single band. So in those bands, you have to make a lot of assumptions. So more than half of the data is very, very dependent on what those assumptions are, particularly assumption on something called the beaming parameter, which we'll talk more about. There's also a bunch of fairly unlikely combinations where you have, in this case, there's 9,000 asteroids that are estimated with the W2 band alone. W2 band is about 50% thermal, 50% emitted. So in order to use this by itself, you have to make an estimate of what is the IR albedo. And since that IR albedo totally determines the result, you've assumed the result by assuming that number. So those are a little bit unusual. Now, in the PDS version of the NEOWISE results, they have a model code, and that's how we know there's those 10 models. And this is what the model code is. The first is D means that they fit the diameter. If they didn't, then there's a dash. V means that they fit the visible band albedo. B is the beaming parameter, which is eta, which isn't phonetic, but you think beaming. And IR means that they fit the IR albedo. And this shows you what the bands are. And this also shows you what the typical reflected sunlight is for a couple of different emissivities. You can see in the W1 band, it's essentially all reflected sunlight. In the W2 band, there's this mix, and depending on what your emissivity is, this is the thermal emissivity of the typical main belt asteroid temperature. You'll get a different mix. Then it's W3 and W4, where the reflected sunlight is so limited that they really are thermal. So there's about 69,000 results that make an assumption about what that IR albedo is. There's about 1,000 that make assumptions about essentially everything except the diameter. Now, in order to make that assumption, you have to come up with some way of guessing what that IR albedo is. So this is the approach that the NEOWISE group took, where they say the IR albedo is A times the visible band albedo, because visible band albedo is something that they would get from the analysis. And then A is a constant that's supposed to be a constant on a per paper basis. So they have one constant for main belt, one for near-Earth asteroids, one for Jupiter Trojans. Well, except, actually they don't. This is a plot of a histogram of that parameter A for various groups. And in most of them, some of them, this is probably a rounding thing, where 2 is the parameter for the Jupiter Trojans, and there's some set of things, but they're very close to being 2. For NEOs, that's not true. Some of the ones that use an assumption are below 1, and some are above 2.5. So there's, having made the assumption, there's also a lot of special cases that deviate from the assumption.
Is it possible they use different p-value for different taxonomic classes, class groups?
It's a good idea. I haven't checked that. That is a possible thing you could do. Now, the main problem with picking that value A is this is a scatter plot for main belt asteroids of the IR albedo versus visible band albedo for the cases where they fit both. And they're really not very much like each other. This is the line that's at a slope that they chose for main belt asteroids. But the problem here is no matter which thing you pick, a linear relationship just isn't a good one. I calculated what the best fit line is and so forth, but no matter what line you put through here, you have very considerable scatter. I mean, you here, look from down here at 0.2 up to 0.8, and that makes a huge difference in the assumed flux, and so that makes a big difference in the diameter.
Excuse me, I don't understand. Were those parameters independently determined?
So when they had enough bands, when they had all 4 of the bands,
Yeah.
they would independently determine them in a curve fit. So they could independently determine what is the IR albedo, which would be in the
Right.
W1 and W2 bands, versus the visible band albedo, which you get from the diameter that you get from the thermal modeling, and from the visible band absolute magnitude H.
So they're not independent because you have to get the diameter from the IR. So, I mean, or let me rephrase the question. How many asteroids do we have a visible albedo determined for, independently of any assumptions?
Well, really independently of any assumptions, not very many.
That's what I thought.
Like a few hundred.
Right.
And that's from radar primarily, and from stellar occultations, and from a very few, because we know Sirius pretty well now. This is this table here is if you did try to make the best fit line and make a linear relationship, what you discover is that the best fit is a very different number than this. The other thing is that if you look over here and you do a statistical test, a line that has a constant term also is a much better fit in most cases. So if you're going to make a linear assumption, that would be the better linear assumption to make. But any linear assumption has this problem that, and you kind of know that has to be true because of the suggestion that someone made a moment ago about different taxonomic classes. We know that you can separate asteroids by their spectra. So it shouldn't be surprising that the IR albedo, which is different. That's kind of part of the game. So another thing that you might do is you might guess the beaming parameter that's in the NETA model. That's this thing, or in the here. You can see this is an enormous number. Assume a difference in both the IR albedo and eta. Well, this is the next problem is that they don't actually line up with the actual values very well. So each paper makes an assumption about what that beaming parameter is. that assumption is in some cases fairly close to what the mean is across the thing, but there's a wide range of variation, and for some of them there's quite a few that have very, very different values. This was maybe one of the more surprising things. Most of the NEOWISE data has not been analyzed. They went through a process where they took the data and they would discard data for one reason or another. We'll talk about the reasons in a moment. In the full cryo portion of the mission, 23% of the asteroids were observed in all 4 bands. But by the time they were through throwing the data away, only 3% remained. So all the data in all of these other cases was originally data where they had all 4. And for one reason or another, they were thrown out. In fact, some of them all the way down to only 1 band being left. Now, there's sort of 2 reasons for this. One is that they would divide the, they'd only do analyze, rather than all of the data you have on an asteroid, they would only analyze it in 3 to 10 day epochs. Some papers say 3, some say 10, so apparently it was on a per paper basis. This winds up discarding a lot of data because you're only analyzing the stuff that fit in that epoch. But the other thing is something that I call the 40% rule, which is you take you count how many observations you have and you discard an entire band of data if it has fewer observations than 40% of the maximum. Now, here's the problem with that. If you just take all of the observations they did overall, this is the statistics, this is simply because of the sensitivity of their sensors and the typical brightnesses of asteroids. You know, it's only reflected light over here, so it's going to see W3, W4 the best. So if you took this rule that said I'll discard anything as less than 40%, if you did that on the overall basis, you'd never use those bands. Here's a couple of examples. So these are the data points that are plotted. Gray means they were thrown out by the 40% rule. These dashed lines are the sensitivity thresholds. So here you can see some, in this case you've got points which are very close to the sensitivity thresholds. They're below, so I think they're valid data points. Those are kept. Here you have points which are pretty much the same distance from those sensitivity thresholds, but those are discarded because you've got so many more of that W3, that W3 being 177, pushes those out. Now the stated reason for this is to avoid cosmic rays. And I don't understand quite how this avoids cosmic rays. Because you'd think cosmic rays would either be an anomalously bright detection, and it would be a point. It wouldn't be a reason to throw away an entire band of data. Well, here's another thing that was unusual. This is a direct table from one of the papers. This paper quotes the diameter down to the nearest meter. Well, there's a whole bunch of them that were exactly kilometer resolution. So I looked, and it turned out that they are all asteroids which were measured by what I call ROS, radar occultation spacecraft. So those are the asteroids where we have the independent determination of diameter. And in 129 cases for 105 asteroids, it matches to the nearest meter. So now, I did a Monte Carlo to say that's about 10 to 210th probability of happening by chance. this is the other interesting thing. So I put a preprint out that said this. That was before the PDS thing was taken. And when the PDS, these things came out in PDS, I mentioned there was a bunch of things that were deleted. Well, one of the things that were deleted were the copied diameters. Except for 9 results. There were 9 results that were in there, and they have the model code -VB-. By the way that model code works, this means the diameter was not set by modeling. So though it was a model code that was for the case of copying the diameter from another source. Now, the problem with copying the diameters from another source is, how do you determine the accuracy of NEOWISE? Well, you compare to those other sources. But the only result is copied, so you can't compare them. Now, I think the argument they might make is that this allows them to estimate other parameters better if they chose those things, but you kind of ought to do it both ways, because if you do it both ways, then you've got an opportunity to go and check and see what the errors would be. So Jean-Luc actually posted on a Yahoo thing, sort of at the same time that the PDS compilation was being posted and the diameters were all being deleted, Joe Massiero is confirming here that it was perfectly fine that they did it, and it's because that means they would get a better estimate of the meaning parameter. Which, if that's really what your concern is, that's great. I think most people would be more interested in the diameters, so it'd be useful to have the diameters as a point of comparison.
So, any comments?
Yeah.
This was supposed to do the minor planet mailing list.
Yes.
And I guess the question is, it's fine if you want to use the diameters that way, but you should state so in the paper. Of course. And that's the problem.
Well, yeah.
That they didn't.
Yeah. Well, that's, yeah, they did not, if that statement had been in the papers, then it'd be one thing,
Right.
but it wasn't. I mean, if we went back up to that chart that had all little zeros on the things, that says thermal fits.
Right.
So here's another thing. This was an idea that was due to Josef Hannes and people. The WISE, of course, was making a map of the sky, so it takes successive frames. Well, there's an overlap, of course. So that means about 10% of the asteroid observations are in that overlap. That means you get 2 measurements within 11 seconds. 11 seconds is too soon for almost any asteroid to have rotated significantly or something else happen. So it gives you a way of estimating what the instrumental error on the WISE observations are. So here's what you get. So in this case, X and Y here are the one measurement and then the second measurement. Of course, that's the line Y equals X. And you can see there's quite a bit of scatter. Interestingly, if you look at the WISE pipeline estimate of the observational error, that jumps around a lot too. So this is the sigma of those. Now, what you can do is you can make a statistic, which I'm plotting here. This statistic, if you've got 2 things drawn from 2 normal distributions, if you form this statistic, you should get a normal distribution with unit standard deviation. So here I have colored those charts by this statistic, and this color here is 8 sigma. And we've got lots of 8 sigma points. That's sort of a hint. In fact, if you look at the maximum standard deviation there, it's 46 sigma. Now, this tells you it is not a normal distribution. When you get 46 standard deviations out, there's something seriously wrong. And so here's what the statistic is. It's actually best fit by a generalized student's t-distribution. And here's the reason for this. student's t-distribution has got this long history in statistics. It comes from making a small-sized sample of a normal distribution. And a student whose actual name was William Gossett, who was the head brewer at the Guinness Brewery in Dublin, was interested in using statistics to analyze the quality of beer. Now I went to the Guinness Brewery and I said, "Do you have anything here about William Gossett?" And they said, well yes, but you're the first person who ever asked." And they had a little picture of him, but only as chief brewer. They didn't say, "Oh, by the way, he was student of student's tea." So,
I
yeah?
want to make sure I understand. So the plots you showed was for the discrepancy between two consecutive measurements in that
Yes.
overlap band. So is the error estimate incorrect, or?
Well, here's what it is. In each case, the WISE pipeline will estimate the standard deviation from the photon statistics. It is, in fact, a small sample size of a normal, really a Poisson, but effectively a normal distribution. So if you think of that instrumental sigma as being the true sigma, it isn't. It's an estimate of the sigma, and it happens in that case the estimate's fairly poor.
You're
Now,
talking about only like several dozen photons sometimes. Right?
Yes,
So
well-
there's a lot of fluctuations in that.
Exactly. And
So it's
the
not guessing.
WISE, the WISE mission was originally designed to do 8 to 12 co-added frames. Now, by the time you do that,
It's fine.
you're fine. You're totally fine. But for asteroid observations, they had to take a single exposure. And when you take the single exposure, you've got a problem. Now, if you use maximum likelihood and you fit the best normal here, it's got a sigma of 2.45. That means the estimates in that band are at least a factor of 2.5 worse than you think they are. Now, it's worse than that really because you've got this tail of things out over here. And the problem with that is that the error analysis that was done assumes a normal distribution with the WISE sigma. I think this also, it was an issue with some of the curve fitting, which we'll see in a moment. If you do a chi-square fit, where you're dividing the square of the difference by the square of your sigma, that only works if you really have the correct sigma. If your sigma is too small, you will over-constrain your fit and you will not get a fit. And I think that's why they divided the thing into those 3 to 10 day epochs. And I think that may also be why they had that 40% rule, is they were trying to constrain the variation. There's actually yet another problem, which is besides the instrumental error, you also have a sampling error because the asteroid has a light curve. And the typical light curve variations are a factor of 2 bigger, at least, than your single measurement errors. So you're not going to be able to get a fit if you do a chi-square. So this is one of these funny cases where chi-square leads you astray. I think that's why all of this happened. Because there's this phenomenon, it turns out a lot of the curves don't go anywhere near the data. So here's the data for 4 bands. This red curve is the curve that the NEOWISE did. It misses every data point. Here's one where it hits. Here in this case, it's this one. It hits every data point, but it's kind of funny. Now in both cases, here I've drawn a straightforward best fit. So you certainly can fit them. It turns out that this is quite a few of the results. If you look on a percentage basis of the single band results, about 30% of them miss the single band they have. So it's got the problem that first of all it's a single band, but second of all it doesn't actually hit the data points. In the ones where you've got all of the data, about 60% hit all of the data points. And that's normally what you would think would be a reasonable result. Now this is using an extremely crude measure of hitting the data point. What I mean by hit is it has residuals of both signs. Now obviously you can have residuals of both signs and still have a lousy fit, but this is for the cases where all of your residuals are one sign or the other. Now, when I first found this, I thought, well, gee, I must have done something wrong. I must be calculating my flux incorrectly. So here are the residuals. And the residuals are actually really good. So what this says is, even when the NEOWISE curve misses every data point, it's missing every data point from below just as often as from above. It also means I'm calculating the flux correctly, because otherwise you'd see a huge systematic shift where those would be very far from zero. Okay, here's another issue. This is the definition of geometric albedo. You have the diameter of the asteroid in kilometers, the absolute magnitude h, that's what it is. Well, we can check this by saying, well, let's take the WISE D and the H. They list the H that they used, which is good because the minor planet sort of changes H all the time without warning. So you can look at the absolute magnitude here of the difference in diameter or the difference in albedo. Now, you don't know if a point is wrong. Is it wrong because it has the right diameter and the wrong albedo, or the right albedo and the wrong diameter? You don't know either one. But here are the absolute errors. Here's the proportional errors. And the interesting thing about this is most of them work fine. So most of the data points are great, but about 14,000 of them, or 15,000, don't work, and some of them are quite extreme. This is more than 100% error in PV, or more than 100% error in diameter. And this must have been caused by something which varied the albedo separately from the diameter. Because if you had determined diameter and then plugged in albedo, this wouldn't be possible. So this has got to be something else going on. So finally, what we can do is we can say, well, okay, how accurate are the results that we have? And you've got in this case, what you do is you take these diameters that come from radar, occultations, and spacecraft. Fortunately, there's a lot more of them now than there were in 2010 when they did the analysis. The trouble is we don't have good statistics on all of the combinations of bands. So in this case, for the W1234 band, we've got 435 cases, so we got pretty good statistics. Almost half of the results are from the W3 band alone. We only have 17, so that's kind of a lousy figure. We've got no idea if those 17 are very lucky or very unlucky. But what this suggests for the ones where we do have a reasonable amount of data is that you've got a systematic error of about 5% here. And you've got a random error, which is roughly twice the better than 10% that was claimed. Maybe it's 1.5 times. Now that's still not a terrible figure, but I think it's better to know what it is. It's also, this illustrates the problem with trying to treat it as a unified whole. Some of these are low, systematic error by 5%, but some of them are much higher. Some are as high as 23. Now, that's based on a single thing, so that could be very wrong. what you'd like to do for something like this is be able to take all of those cases and then say, well, gee, I can subsample them to make some of those. That way I could have 435 in all of them, but they didn't do that, and I haven't been able to recreate their analysis. They don't say a bunch of stuff that would be necessary to replicate it.
So does that mean we have 1,000 independently determined diameters for asteroids, and you've compared those to the NEOWISE estimates? Is that?
Well, yes, but no, not quite. There may be some double counting, because there are some asteroids that were, particularly an asteroid which was observed in the post-cryo phase could be in W1, W2, and in the cryo phase up there. So it's probably not 1,000, it's probably more like 500.
Those fluxes are all published, W1, 2, 3, 4 are all...
Yes. Yes,
So you could do the extraction yourself.
Well, I could do the curve fit myself. I have. I can't get their answers. There's something about it that isn't replicatable. So this is maybe a little hard to see. This is here I'm plotting the NEOWISE versus, in this case, versus Akari. This is versus a paper by Ryan and Woodward. This is versus IRAS, and that's versus the radar occultation and satellite ones. The key thing here is that if you look, these are color-coded by the different models. And the impression to take from this is there are certain regions where you only see some colors. Because those were asteroids that were, for example, hard to see. If they're very far away, if they're Trojans, you might not get as many of the bands as you would with another kind of class of asteroids. So you see that you get these clusters of color, which means that you don't have a uniform distribution of your model versus your diameter. They're correlated. And that's not surprising. Large asteroids in the main belt are easy to see. Large near-Earth asteroids are easy to see, but there are not that many of them. Stuff that's really small and really far away, you tend to not be able to do as well. So anyway, I think the biggest conclusion from this is that the analysis of this data isn't a solved problem. That there's a lot more interesting data that could be wrung out from this. And I think it would be really useful if this was something that could be replicated and a little bit more open than it's been. Because you'd like to be able to do a lot of different searches. Let me tell you a couple of the things I have been interested in. There's a couple of asteroid models. One is the near-Earth one. There's another one called the fast rotating asteroid model, FRM. I derived a model for a tumbling asteroid. Turns out if you tumble in two directions, so you've got two different axes of motion, which we know there's a few asteroids that do, but there's probably more. If you tumble in two things, the spectrum changes. In fact, the spectrum, it's very simple, it becomes a black body. And if you think about it, that's straightforward. Rather than having an equatorial phenomenon where the subsolar temperature is very bright, you're distributing across the whole asteroid. So you ought to be able to find fast tumblers. You ought to be able to find all kinds of other interesting things from this data. So I think that there's a lot of data to be analyzed.
Thank you.
Questions for Nathan?
Yeah.
So looking at the NEOWISE data, in the past, and I was working with Ned Wright, there was a discussion of, and I know you like dinosaurs too, so we're going to put
Well, this is my T-shirt that adds both dinosaurs and asteroids together in one shirt.
So decades ago, there was a discussion that there might have been this crazy object called Nemesis that was possibly a red dwarf star that caused the extinction of the dinosaurs. And then they found that, okay, there was no red dwarf data, this thing doesn't exist. But then, looking at the statistics, Matisse and Whitmer, they said that there's an object called Tyche. Tyche might have been the new Nemesis, and it might exist in the data. I was working with Ned Wright to process a lot of that data. And the other thing too, that I don't know if you have access to this, is that I went to JPL and I got a fellowship with NASA. So this is my new device to look into the NEOWISE data. And I'm working with NEOWISE data. So if you need any help with this data, let me know what I can do. I am looking for objects that might have been overlooked. I know you're working on albedo stuff. That's not quite what I do, but we can help each other, so let me know. And what are your thoughts on Nemesis and Tyche? Does this thing exist? And how about finding Planet 9 in the data? It might be there.
So it turns out that, forgive the pun, but this idea just keeps coming around periodically. There's a physicist who's mostly a particle physicist who's written a book. Lisa Randall's her name. She's written a book suggesting that in fact
dark matter might have caused the extinction of the dinosaurs.
Well, what all of these things are about is trying to come up with a mechanism for what might have caused or been a sort of approximate cause of the asteroid impact. The idea of Nemesis is that it would perturb the Oort cloud and send something in as a one-off.
And then what Matisse and Whitmer said, that there's a statistic that says that a bunch of comets are coming statistically, so we assume that what is perturbing this thing is Tyche.
Yeah, so so those are both things that say, hey, we've got some perturbation in the Oort cloud that sends stuff in. Now there's another set of folks who say, no, actually there was a collision about 160 million years ago, I think in the Baptistina family, that may have led to the Chicxulub impactor. And they have a sort of a dynamical argument that's based on that. I think it's clear that you can get impactors without there being anything. You know, the Chicxulub happened, and we have lots of craters on the moon and other places. Bill Botke gave a very interesting talk recently at the last EPS on there's been a mystery as to where are all of the missing craters on Earth that you think you should see a lot more on Earth. And he had some very interesting data from the moon suggesting that in fact the bombardment rate had actually been lower in the past. And that those craters aren't missing, they didn't occur. So I think there's an awful lot that you could come up with. The advantage of Nemesis or Tyche as an explanation is we know that there have been a lot of mass extinctions on Earth. And so the first shock to geologists was, hey, maybe there was an extraterrestrial cause, right, for the mass extinction. In fact, after getting my degree in this department, I went to Princeton in physics, and it was in 1980, and I was in one of the first talks that Louis and Walter Alvarez gave on their theory that an asteroid killed the dinosaurs. And a huge set of dinosaur people didn't want to believe it. But then, the next impulse after no is maybe that's what causes everything. And it's a natural enough thing in science. And the Nemesis thing was originally based on someone taking the Fourier series of a bunch of extinction data, saying, okay, there's a whole bunch of extinction data that seems quasi-periodic, what could cause that? And that's what what led to that.
To get back to your talk though,
Yeah.
so, although that's interesting, you have this comparison with the occultation profiles and a scatter of 15 or 20% or something
Yeah.
like that. How much of that is due to shape? I mean, they're just
I don't know,
instantaneous.
it's a really good question,
Yeah.
because when you sample, that'll depend on how many points you have in your data set, right?
But probably the occultations are just one or two times, right? One or two events.
Well, the really good ones
Yeah.
will actually try to get a shape model.
But it's still only the instantaneous projection of whatever shape
It's an
it is.
instantaneous projection of one, and for a couple of them, they will have that twice.
Yeah.
You're right. So it's not perfect. But the way you could determine that statistically would be, if I go back up to where there's some data. Well, here we have a pile of different NEOWISE observations at, this has got the distance from the sun in AU, but if you plotted time, it would be something pretty much similar. You have to, and of course, here's what your trend line is. Well, variations off of that trend line would tell you what the light curve is. So if you had a better curve fit for all of them, you could then invert it to make light curves. It would be very interesting to plot the dispersion against the radar diameters versus what the light curve effect is. That'd be a very interesting thing to do. In general, what you'd expect is that will be size dependent also. That the larger the asteroid is, the more spherical it is.
So if you wanted to do this right, you need to fit for diameter, visible albedo, infrared albedo, and beaming parameter, is that right?
So,
you need 4?
no. So, sort of I should have made some slides on this. You basically are fitting for, normally you're really fitting for one thing, which is two things, diameter and your subsolar temperature. The way people conventionally do that is they have the subsolar temperature be a function of the visible band albedo and also the, what?
Let me see.
Oh, yeah. Wait, so you don't need to do that. In fact, you're better off just fitting that, and the beaming parameter, that was it. You've got the beaming parameter and the albedo, and they appear as a ratio in the formula for the subsolar temperature. Now, in general, in nonlinear curve fitting, having a ratio of two things that you're varying against each other is a bad idea. So you can get a much better fit if you just fit for subsolar temperature and diameter. Then for the near IR albedo, if you're going to use the W1 and W2 bands, you have to also put in either one parameter for both or two parameters if you have both bands.
Yeah, I guess my question was how much, what fraction of the data has enough bands that you can do the fit properly? And of course you wouldn't want to throw away, this 40% rule, you want to get rid of that, presumably.
Actually, quite a bit of it has got enough. Let me go back. One of the other issues with the NEOWISE analysis is that when they fit IR albedo, they assume the emissivity in that same band was fixed, and so that violates Kirchhoffs Law. So if you actually respect Kirchhoffs Law, it becomes simpler. Let me see, back one more. Okay, here we are. So, the stuff that goes through W3, W4, so all of these, about 44% of them, you can get a pretty good result out of. For the W1, W2 things, which you've got a lot of because of the post-cryo mission, where those sadly they're the only bands you can see. You can fit those with this, if you have a Kirchhoffs Law respecting framework, and you have much higher errors, but you still can do something with them. So probably you can get something out of a lot of the data.
Any other questions for Nate? All right, if not, let's thank him again.
Okay.